up in the sky, whether it be a plane, a satellite, or it used to be the space shuttle, and you shoot a radar beam down to the surface of the Earth. It bounces off the surface of the Earth back up to a receiver on the same platform, and you use that to measure the distance from the satellite down to the surface of the Earth. Okay? We just measure the travel time until the energy bounces back, and because we know the velocity of the radar wave, and we can measure the distance. Okay? Very straightforward. INSAR, which is what we're actually going to use, is interferometric synthetic aperture radar, and the interferometric part, is simply that you make this measurement twice, and you use the difference between the two measurements. And that gives you much greater accuracy. Okay? So you shoot the radar down 1 year, and you come back and you shoot the radar down from exactly the same point, and 1 year later, and you compare the return that bounces back between those 2 years. That's the interferometric part, and that gives you much greater accuracy. Okay? And so we can use this, the difference between the phase of the arrival that's come back, to give us millimeter accuracy motion of the surface of the Earth in the direction that we're looking from. That's the key thing. So these satellites, they're typically looking down at the surface of the Earth at an angle of about 45 degrees. We come back a day later, a month later, a year later, we shoot the same ray, it comes back, we do the interferometry, and we can tell whether that point at the end of my arm, at the end of the radar beam, has moved towards the satellite or away from the satellite with a millimeter accuracy. That's the idea behind INSAR. Okay? So here's an example of an interferometric image that is across the Bay Area. So again, here's San Francisco, this is the peninsula of San Francisco, this is the Bay, sorry, it takes a little bit orange, this is the Bay, San Pablo Bay, and then San Jose down here. The red line is the Hayward Fault. This is obviously focused on looking at the Hayward Fault. And then the color here, the grayscale, are regions where we didn't get a good return. You don't get a bounce back from everywhere on the surface of the Earth. The vegetation is the primary problem. But all the colored are places where we get a bounce back, and the red, the maximum red over here, is a range change of plus 4.5 millimeters per year. This was done after a number of years, so I've just divided by the number of years. 4.5 millimeters per year, and the blue is minus 4.5 millimeters per year. Okay? So the fact that it's reddest here and bluest over here, and there's this sort of change as you go across, is telling you that this point over here is moving in the opposite direction to the point over here, and of course we know that, because we know what the motion is, the creeping motion is across the Hayward Fault. Question? Right, so the question was, it can measure horizontal movement and vertical movement. It can measure movement in the direction of the X-ray, the radar beam. Okay? So the radar beam is looking down at about 45 degrees angle. So we can measure whether that point has gotten closer to me or further away from me being a satellite. That's all we can do. And of course, you can achieve that by either vertical or horizontal motion. Okay? So that's one of the limitations here, is that we don't have the motion in 3 dimensions, we just have the motion in one direction. Okay, so that's laid out here, in fact. So what I just said was that across this region here, there's a total of 9 millimeters per year motion. Yeah, question? Okay, so the question is, what's with the blue section here? Let me come back to it in 1 minute, okay? So let me go through this map, and then I'll come back and we can talk about it. Good observation. Okay, so there's a total of 9 millimeters per year, okay, across this whole section, across the Bay Area. So as I've been saying, this is like the satellite is looking at an angle, and we'll assume it's close to 45 degrees. Let's just use 45 degrees. So there's a relative motion of 9 millimeters per year, but at 45 degrees. If we assume that it's all horizontal, that there's no vertical motion, and you do the trigonometry, you get 6 millimeters per year. Okay? So what this is saying is that there's a 6 millimeter per year motion across that entire region that we're looking at. And so that's more, of course. We know that there's a creep rate across the Hayward Fault of 4 millimeters per year in Berkeley. And so this motion is 2 millimeters per year more than that. So obviously we're going further out from the Hayward Fault, so we're seeing more relative motion. Okay, does this make sense before I go back to this blue blob? So this is another mechanism that we have to measure the deformation of the surface of the Earth. Yeah? Why is it? No. So, okay, so the question is, why is the creep along the Hayward Fault 4? Well, when we're getting a number of 6 millimeters per year here. So, of course, the creep along the Hayward Fault, let's see, where's Berkeley? Here's the thing. So the creep along the Hayward Fault is right here. Okay? So you can see that we go from yellow or orange immediately to blue. Okay? So that's the 4 millimeters per year is right there. But you can see, obviously, as we go across San Francisco, it's getting more and more red. So this is a combination of both the creep along the fault and this overall deformation, this S-shaped deformation that is accumulating across the whole region. So we're measuring a total of 6 millimeters per year across this entire region, and at the Hayward Fault, at the stadium, we measure 4 millimeters per year across this region. So that's the difference between the 4 and 6. Okay? Any other questions about the calculation first? All right, so let's come back to this blue blob. Why is there a blue blob on this side of the fault? Because this deformation, this plate tectonic deformation we're talking about, we would expect it to go from red over here. As you get closer to the fault, it'll be more and more orange and yellow, and then you cross the fault and it's more and more blue and purple. So what could be causing this blue blob right here? Well, what is this area? South Oakland, Hayward. Right, South Oakland, Hayward. Yeah? Say again? What? Oh, digging. Sorry. Digging. So, well, that would mean that it's a very large area for people to dig. No, but even so, even if this was construction, this is a very large area that they all decided to, which way would it have gone? The distance has decreased, so it's actually an increase in elevation. Because the distance has decreased, so this actually means that it's the opposite, they would have dumped stuff. But still, anyway, the point is that man-made construction isn't going to operate on this scale, right, in a coherent way on that scale. What, anything else? So it's getting a little bit higher. Any guesses? So long faults, they have sag ponds. Yeah, and the mounds, the opposite. That's right, but that actually happens on a smaller scale. This isn't too large a scale for that, but that's a good thought. Yeah. That's actually a good suggestion. The suggestion was that this could be the locked section, and you can see that obviously there's something going on close to the fault, but it looks like it's blue on both sides of the fault. There's no step change. So that could be part of it, absolutely. And in fact, this is the section where it's locked to depth beneath. But that's actually not the main cause. The main cause is aquifers. Okay? And as aquifers, subsurface aquifers, increase the amount of water in them and dry out, they actually can cause pretty significant increase and decrease in the elevation. And so that's actually what the cause of this is. Of course, this is in the opposite sense. This is lifted up. So this would imply that an aquifer was filling over this time period, i.e. this was taken many years ago, not in the middle of the drought that we're in right now. Okay? So the point is that there are other signals that cause deformation of the surface. It's not just plate tectonic. Aquifers are one of the things that can cause deformation of a very large area. Okay? This is a significant upward lift, what's the right increase in the elevation of the land surface. Of course, you don't see this at the surface because this is happening over a very large area. So it's not like you're going to see cracks in buildings and things like that because you have this very large area that is lifting up. Okay, good observation. Let's keep going. Okay, so now we understand how INSAR works. We can use it to measure these deformations. I want to show you, first of all, a volcanic example. So So this is the Three Sisters uplift that occurred in Oregon, I guess a little more than a decade ago at this point. But it was a very nice example where we could use INSAR to measure the deformation of a volcano. And so these are what are called fringes. So it's interferometry in that you can measure the difference in the phase of the arrivals. Those of you who are physicists or have physics background will know what I mean. Those of you who don't, you don't have to worry about it. The point is that it's a cycle. It's a cycle. And so that what's plotted, the way we plot these interferometric images is that we plot this sort of repeating color scale, each that represents one wavelength. So all that matters, the actual takeaway message that you need to know, is that when you go in look in one of these images and you go from red to red, that corresponds to a change in distance of 2.8 centimeters, because the wavelength of the radar is 2.8 centimeters. So you can count the cycles. So you count from red to red to red to red. So that's 4 cycles. Each of those cycles represents a 2.8 centimeter change, and you get the total change. Okay? So we have about 4 cycles here. This is the center of the volcanic system. We have a 4-cycle change. 2.8 times 4 is about 10 centimeters. So there was about a 10 centimeter uplift of the Three Sisters volcano over the course of this 15-year period. Does that make sense? Okay, so the idea here is that you've had this uplift. You see this in these cycles. You can count the cycles, 4 cycles, and that corresponds to a total of a little more than 10 centimeter uplift. 4 times 2.8 is not 10, but it's close to 10. Okay? And so this happens because as magma chambers fill in the Earth's crust, it actually causes an increase in the elevation at the surface of the Earth. Of course, the question then becomes, if you see this uplift, does that mean that we're about to have a volcanic eruption? And when INSAR was first being used, which was around about this time, this was one of the first examples where people were able to use INSAR to see deformation of volcanoes. Of course, people started looking at all these volcanoes, and lo and behold, they were seeing these uplift patterns at many volcanoes. And for a while, there was a great deal of concern that we were about to have a lot of volcanic eruptions. And of course, and that didn't happen. There were some, of course, but not many. Most of the cases where we see this uplift beneath a volcanic system, there was no volcanic eruption following. And instead, it would then just deflate. So in fact, what was happening was that magma was coming up, filling a magma chamber, and that was causing the uplift. But then the magma would sort of percolate out horizontally into the crust and would essentially cool and solidify in the crust, so that the uplift beneath the volcano would decrease because the magma was going horizontally, but there would be no eruption. Okay? So that's volcanoes. But back to earthquakes, here's another example, another early INSAR image following the Landers earthquake that occurred in 1992. I think this was actually the first time INSAR was used to measure the surface deformation that occurred during an earthquake. And so remember, these are interferometric, so there's 2 images. So they had one radar image that had been collected a month or 2, I think, before the earthquake, and then they took another image a month or 2 after the earthquake, and this interferogram is showing you the total amount of deformation that occurred between the 2 images, which primarily is the deformation that occurred during the earthquake. Okay? So this is a Landers earthquake in Southern California, so this is a right lateral strike-slip fault. You can see it's right lateral just looking at this image. And so the fault in this map is right here. It's the red zone, the little arrows, to show obviously the right lateral motion on the fault. And so when we look at this, we can actually estimate what was the total slip along the fault. And the way we do that is by counting the fringes. How many fringes of movement are we seeing? So I'd like you all to go ahead and count the fringes and estimate the amount of deformation. I'll give you a minute. You can talk to your neighbor. Okay, so how many are people seeing? 12? 7? Anybody else? 10? 12? It's good, we could do a statistical average and I think you'd be about right. I can see 8. Okay, so the way you do this, it's not that straightforward, of course, but you sort of start out here and you count the fringes back towards the fault. I mean, you go in the other direction, I guess. So if we start here with this purple or blue, whichever, we go 1, 2, 3, 4, 5, 6, 7, 8. Okay, I mean, I would count 8, maybe you can argue that there's 9, whichever. Okay, so the total amount of deformation is what? 8 times 2.8, which is 22, 23. Okay, so about 22 centimeters of motion. So what this is saying is that this point, close to the fault, has moved 22 centimeters in this direction and has pushed this lobe of the crust out. Right? So this has moved at least 22 centimeters, I should say. So this piece here, very close to the fault, you can't see fringes anymore. It's sort of all speckledy. And the reason for that is that you can't see coherent signal. And the reason you can't see coherent signal is that the surface has all been deformed, and so the surface has moved too much with respect to when the first satellite image, or the first radar image was taken, and so you can't see a coherent change, and so you get this speckledy image. So it's a low estimate. So the actual slip of the Landers fault along the fault was more than 22 centimeters, is what we can take from this. Okay? But this is actually very valuable data because the shape and the shape and geometry and how far out this deformation extends tells us about what's happening at depth. It's not just telling us about what happens at the surface of the Earth. It allows us to model the deformation on the fault at greater depth. Okay, so very quickly I'm going to take 5 more minutes, and I want to talk about interaction or the role of fluids and earthquakes, a slightly different topic, becoming an ever more important topic, as you probably heard the discussions of induced seismicity that are going on right now. Oklahoma has a seismicity rate that is almost the same as California's. As you know, California is on a plate boundary. Oklahoma is not on a plate boundary. So much of that seismicity in Oklahoma is induced seismicity. So the fact that there's so much seismicity is quite alarming. So this induced seismicity is usually related to fluids in some way. So first of all, I want to explain why fluids and earthquakes are related to one another, or how fluids affect earthquakes. So obviously you've all seen rock outcrops, and you've seen that there are many fractures in rocks. Rocks are also made up of grains, which means that there are often pore spaces between the grains in a rock, and so those pore spaces can be filled with fluids. And of course, then on a larger scale, you have faults at the surface of the Earth, which of course are a way that fluids can enter the Earth's crust. So there are lots of fluids percolating through the Earth's crust. Now, the role that fluids have in helping facilitate earthquakes comes down to hydrostatic fluid pressure. So hydrostatic fluid pressure is simply the fact if you were to go and drill a well, okay, if you drill a well right here, so you cut out a column of rock, however wide, 6 inches in diameter, and let's assume that it's full of water, just because there's an aquifer, and so the entire column of rock is full of water, the column of the well is full of water, then the pressure of the water at the bottom of the well is what we call hydrostatic fluid pressure, okay? And it's simply the fact that you have this column of water, right, and for every inch that the column is longer, the water pressure is greater. And the total pressure is just the density times gravitational acceleration, right, density, rho, g, gravitational acceleration, times the height of the water column. So as you go deeper into the Earth's crust, hydrostatic fluid pressure increases. Okay? And it becomes, if you know how heavy water is, it becomes very high very quickly. All right? So you get an increase in the fluid pressure with depth. And so if you now imagine these pores of a rock and these fractures in a rock and faults within a rock, then as you get more and more fluids, then you increase the hydrostatic fluid pressure, you can start to push the rock surfaces apart. So imagine a fault plane, you have high fluid pressure, it's pushing the fault plane apart, and you can imagine that the strength of that fault plane is reduced. So we're building up stress on the fault plane all the time. If you introduce fluids, you push the fault plane apart a little bit, you're more likely to induce an earthquake. All right, so that's the relationship between fluids and earthquakes. You introduce fluids into the Earth's crust, you're going to increase the likelihood of having an earthquake, whether it be a tiny, tiny little micro-earthquake or potentially a larger, damaging earthquake. So there are examples of this. This comes from Colorado, where in 1962 to 1972 there was a swarm of earthquakes. This is a terrible map, I'm sorry, but this is Denver here. This is the Rocky Mountain front. Okay, so this is the mountains. Those of you who've been to Denver, these are the mountains, these are the plains. Denver sits right here with the Rocky Mountain front. And between 1962 and 1972 there was a swarm of earthquakes. There's been very few earthquakes. You don't expect earthquakes in this region. It's not a plate boundary. But there was a swarm of earthquakes, the largest of which was a magnitude 5.3. So that's now at the level where you can start doing damage in earthquakes. And so this earthquake caused about $1 million of damage. There were a total of 12 earthquakes in this swarm that caused damage. Needless to say, people started to pay attention. People wanted to understand why this earthquake swarm had started. Well, it turned out that there was, so here this is the state capital, so this is Denver, okay? And then this is called the Rocky Mountain Arsenal, a military base. And so on this Rocky Mountain Arsenal, they'd actually been pumping fluids into a well to dispose of them. These are contaminated fluids, and so they would pump them into this well as a way of disposing of these fluids. And what they realized was that the earthquake swarm was related to pumping fluids. So here's just a time history, 62, 63, 64, 65, and then the number of earthquakes per month, and then millions of gallons pumped per month. And you can see that there's a correlation between these two plots. So there was more pumping here, there was an increase in activity, more pumping here, increase in activity. They stopped pumping because they started to become concerned that their pumping might be related to the earthquakes. And sure enough, the earthquakes largely stopped, and then they started pumping again a year later, and lo and behold, the earthquakes started increasing again. So it was actually the pumping of fluids into the subsurface, into this fault system that was causing it. And of course, then they started to map it out. They didn't think there were any faults in this region, but there's this big scarp, as it turns out, that had not been identified prior to this. This is the well, this is the Capitol building, this is the fault scarp, and there's actually a facility, I forget what it was, I think it was on the previous map. Oh, I'm missing the... Oh, it's here, right. So this is the Superfund site. So this site here was actually a highly contaminated area that was right on the fault scarp. So people became very concerned that if you now cause a rupture on this fault, you could actually have even more devastating of an impact. Okay? Needless to say, people recognized that these two were related, and they stopped pumping fluids into the subsurface. But this shows how pumping fluids in the subsurface can trigger earthquakes. And this is another example. I'm not going to go into this. Is from the ranging oil field. This was more of a controlled experiment where they increased and decreased the fluid injection and showed that there was an increase and decrease in the number of earthquakes. But there was no question. You could actually use fluids, pump fluids into the subsurface. This reduces the strength of the faults, causes the faults to release a little bit. Okay? So this then led to the question, in fact, somebody in this class, I forget when, already asked me this question. Can we use this approach to relieve the stress that is accumulating on faults? So if we pump fluids into the subsurface along, let's say, the San Andreas fault, will that release the stress? Any thoughts? I heard somebody say something, but I didn't hear what it was. It would lubricate the fault. Okay, so if you lubricate the fault, that's a good way of thinking about it. Think of it as lubricating the fault. What will then happen? It's going to slide. You're going to have an earthquake, right? And so the question is, when you do this, when you lubricate the fault, what size of earthquakes are you going to create? Well, the first thing that comes to mind for me when people ask this question, I think I already mentioned this, was the James Bond movie, A View to the Kill, where the whole idea was that the evildoer in the movie, this guy, was essentially going to destroy much of San Francisco and the Silicon Valley in order to increase his business dominance in this domain. And the way that he was going to do it was by pumping water into the San Andreas fault and then setting off some sort of big explosive to trigger a big earthquake, which of course, as often happens in these movies, would cause San Francisco to sink into the ocean. You know that that's not what happens, although it would destroy San Francisco. The point is that if you were to start doing this, yes, you may well help release the stress on the fault, but the stress on the fault is still going to have to be released through sudden deformation. So you could well be triggering the earthquake. Think of the liability implications. So nobody is going to use this kind of approach of pumping fluids into faults because they actually may be the cause of an earthquake. They may cause an earthquake to occur today that may not have occurred for many decades. So this is not a feasible solution when it comes to dealing with the earthquake problem. Okay, quick question. Great question. Once the big one hits, let's say we have a magnitude 8, like 1906, on the San Andreas fault today, could we then start pumping fluids into the fault to keep it lubricated? So we just released all the strain, we keep it lubricated, essentially encourage it to creep. The challenge with there's probably engineering challenges, first of all, but let's put those to one side. The other challenge, the scientific challenge with that, is that when you do have a big earthquake, it is not clear that you've released all of the strain. We do not think that when you have an earthquake, that sets you back to zero stress on the fault. So by pumping fluids into it, you may accelerate or increase the number of aftershocks. There may be parts of the San Andreas fault that didn't rupture wholly, and you would then be initiating, so it's exactly the same problem. Okay, we'll stop there. See you all on Thursday.